right. So D is a diagonal matrix, right, where the diagonal entries are your eigenvalues if ideally or otherwise known as singular values, right. V is a V is a P cross P matrix which has your eigenvectors, and U is a N cross P matrix which typically spans your column space as X, the same column space as X. Okay. So this is essentially your singular value decomposition that we talk about. So if you look at singular value decomposition or what is called the principal component analysis literature, you will find the following. You will find that they will talk about the covariance matrix S. Okay, what is the covariance matrix? Right, so it is a covariance matrix. This is essentially, if you think of whatever we have been doing so far, what would be this? Centered, right, it is centered. So I take the centered data, okay, then this becomes this right. So X then what I do is I find the eigen decomposition of that. I find the eigen decomposition of the covariance matrix, right. So I can essentially write this as so the same V and D that I wrote here, assuming this was okay. So if I take XC, so basically I am going to get the same thing, right. So it is essentially like doing singular value decomposition, right, and retrieving the V matrix, right. I am essentially taking the X transpose X, which is the covariance matrix of the centered data, okay, and I am finding the eigenvalue decomposition of that. Okay. So D squared would be the eigenvectors of X transpose X. So this is standard stuff you should know. Okay. So the columns of so they are called the principal component directions of X. So there are a couple of nice things about the principal component directions. So we will talk about just one. So I will actually come back to PCA slightly later, right, when I talk more about generally about feature selection, not just in the context of regression, but when I talk generally about feature selection, I will come back to PCA and tell you, at least show you why PCA is good, right. Now I will just tell you why PCA is good. Okay, I will come back later and then I will show you why PCA is good, right. So suppose I take, right, so where V1 is the eigenvector corresponding to the first eigenvalue, right, the eigenvector corresponding to the first eigenvalue. So essentially what this means is I am projecting my data X on the first eigenvector direction, okay. So the resulting vector Z1, okay, will have the highest variance, okay, among all possible directions in which I can project X, right. So what does that mean? suppose this is x, okay, this is not x and y, okay, so it is a 2-dimensional x, okay, this is x. Now I am claiming that V1 will be such that when I project x onto V1 I will have the maximum variance, right. So in this case it will be some direction like this, okay, and projecting x onto this essentially means that right. So you can see that the data is pretty spread out, okay, it goes from here to here, right. On the other hand, if I had taken a direction, let us say, that looks like that, right. So if I look at projection of the data, right, so you can look at the spread, it is a lot lesser in that direction, okay, than in the original direction I did the projection, okay. I know it looks pretty confusing to look at, but people can get my point, right. Right, so in the original direction that way the data was a lot more spread out as opposed to this direction where the data is a lot more compact when I project it onto that direction. So that is essentially what I am saying. So Z1, right, is essentially the projected data onto that direction onto x, right. So Z1 actually has a highest variance among all the directions in which I can project the data, right. And consequently you can also show things like if I am looking to reconstruct the data, original data, and I say that you can only give me one coordinate, right. So you have to summarize the data in a single coordinate, okay, and now I am going to measure the data, measure the error in reconstruction, right. If you looked at it, so the error in reconstruction would have been these bars that I did the projection over, right, that would be the error in reconstruction. So I have the original data, so that is the data. So now I will give you this coordinates, okay, now I have to reconstruct the data, right. So essentially this will be the errors, right. So the principal the first principal component direction, the first principal component direction is the one that has the smallest reconstruction error. The first principal component direction will be the one that has the smallest reconstruction error. So we can show a lot of nice properties about this. So I will actually come back and do this later when we talk about general feature selection, okay. But here you can see the first thing, you can see what each one, right, V1 to Vp will be orthogonal, right. So I have gotten my orthogonal directions, right, and the thing to notice is a lot of the variation in the data is explained by V1. V1 has the maximum variance. Likewise you take out V1, right, you take out V1. So now what you have, your data lies in some kind of a p minus 1 dimensional space, right, and the direction in that space which has the highest variance is V2. It turns out that, so V1 has the highest variance over the all data. So in the space orthogonal to V1, V2 has the highest variance, right. In the space orthogonal to V1 and V2, V3 will have the highest variance, and so on and so forth, right. So essentially now what you can do is, hey, I am going to take all these directions one at a time, right, and I will do my regression, right, because each is orthogonal. I can independently do the regression, I can add the outputs, right, I can keep adding the dimensions until my residual becomes small enough, right. Does that make sense? So I will just keep adding these orthogonal dimensions until my residual becomes small enough. At that point I stop. So this is essentially the idea behind. So remember we are working with the centered data, right. So you automatically add in your intercept, which is y bar, the coefficient is y bar, right, and then your if you choose to take the first m principal components, okay, your thing will be theta m zm, where zm is given by this, right, and theta m is essentially regressing y on zm, right. So that is a univariate regression expression, you know that well now. So this gives you the principal component regression fit. Right. So one of the drawbacks of doing principal component regression is that I am only looking at the data, the input, right, I am not looking at the output. So it could very well be that once I consider what the output is, right, I might want to change the directions a little bit, right. So I can give you an example, it is easier for me to draw if I think of classification. Let us say this is the data, and what would be the principal component direction you want to choose, something like this, right. So that would be the ideal direction that you would want to choose, okay. So now what will happen, the data will get projected like this, right. But suppose I tell you that okay, that is fine, let that be. That these three were in a different class, right. If you want to think of it in terms of regression, let us assume that these three have an output of -1 and these 4 have an output of +1, okay. Now if you think of this direction, so the +1 and -1s are hopelessly mixed up, right, the +1 and -1s are hopelessly mixed up, right. So I can't give a smooth prediction of which will be +1, which will be -1. On the other hand, if you project onto a direction like this, right, the variance is small, right, I agree, right, the variance is much smaller, but if you think about it, so all the -1s go to one side, right, all the +1s go to one side. So now if I want to do a prediction on this, so it will be like, okay, this side is -1 and that side is +1, I can essentially do a fit like this, which will give me a lot lesser error than the other case, right. So in cases where you are having an output that is specified for you already, it might be beneficial to look at the output also when trying to derive directions, right, as opposed to just looking at the input data. So in classification you can see, right, in classification this will be say class 1, this will be class 2, and having this direction allows you to have a separating surface somewhere here, right. We talked about classification in the first class, right. So just having a separating surface here will be great, but in this case if I am projecting on this direction, coming up with a linear separating surface is going to be hard, everything gets completely mixed up.